So today blends in perfectly with electron configuration and atomic structure. We're going to be talking about the periodic table. And it's not too bad. This is pretty decent. So what we have to first talk about is there's this guy named Dmitri Mendeleev who's called the father of the modern periodic table. And in 1869, quite a while ago, he put together the periodic table in order of increasing atomic mass. So this guy's name was Mendeleev. So, Dmitri Mendeleev in 1869. And he did this. I mean, unbelievably smart. But as he put it together, he found a couple things that didn't really match up. So what I have is, I'm going to show you the periodic table now. So Dmitri put together a whole bunch of these in order of increasing atomic mass, and everything was working fine. But there were a few things that were out of order. Like right now we know the biggest one that we see that's out of order would be argon, which weighs 39.94, and potassium, which weighs 39.0. So these two, this argon weighs more than potassium. So one of my students said, well, why don't you just switch them around? Well, how's that going to work? You got a metal from group 1 going into a inert gas, group 18, the group right there, and then you have a noble gas, argon, going into a very active group 1 metal. So those two were a little bit different, and so were these two, cobalt and nickel. So there's another way of putting the periodic table together. But remember, this was 1869. This was a really good job by Dmitri Mendeleev. Now, in 1911, an English chemist named Mosley came along, and by that time they had found protons. And so the next thing that I'm going to show you on the board So, Mosley, like I said, was an English chemist, and in 1911, he finally figured out, hey, if I put these in order of increasing proton number or atomic number, it works. So Mosley, in 1911, put together the modern periodic table. Unfortunately, Mosley was a wickedly smart guy. He was killed in World War I. So, those are the two main men for the periodic table. Mendeleev in 1869 and Mosley in 1911. So now we know for sure that the periodic table is put together in order of increasing atomic number, which means increasing protons. Now, we've got to talk about another thing, and this is called modern periodic law. Modern periodic law. This is real easy. Remember, we went over why is gold gold and why is silver silver? Well, gold is gold because it has 79 protons. So the modern periodic law, the properties of the elements, are due to the number of protons. And that's why gold is gold, because it has 79 protons. An analogy is people have 46 chromosomes. If you got 46 chromosomes, you're a person. If you have 4 chromosomes, you're a fruit fly. So basically the same thing. Every element, the properties of each element are due to how many protons they have, and that's called modern periodic law. Now, let's look at the periodic table. It's put together beautifully. So do you see this staircase right here? That staircase separates the metals, which they're 2/3 of all the elements on the periodic table are metals. So the staircase separates the metals from the nonmetals. Okay, that's the first thing. So what we have to do is we have to figure out, see this word group? All these going down vertically are called groups. In the old days, they also called them families. Now, you know a family is all related. So, group 1, that must mean all the elements in group 1 must be related somehow. So how are they related? Well, they certainly don't have the same number of protons. Their masses are different. So how are they related? Well, the big deal is this. You remember that every single element on the periodic table, electron-wise, wants to look like the noble gases. And from the last chapter, you know that the last shell, which is called the valence shell, can only hold a maximum of 8 electrons. So if you have 8 electrons in the last shell, you're good to go. You're stable. So why in the world are these elements put in group 1? Remember, it's called a group or a family. Well, if you look, all the elements in group 1 have 1 valence electron. So shell 1, 1 valence electron. Shell 2 has 1 valence electron. Shell 3, 1 valence. 4, 1 valence. 5, 1 valence. 6 and 7, they all have 1 valence electron. Now, how this works is we'll look at this and then we want to see what's going on. So let's take lithium and sodium. Li3. Now Li3 from the last lecture is 1s2, 2s1, and the dash would be 2 in the first shell, 1 in the second. So this is our valence shell, and it has 1 electron. So any element that has 1 electron in its valence shell should be in group 1. So let's try a different one. Let's try potassium, which is K19. K19 got 19 electrons. 1s2, 2s2, 2p6, 3s2, 3p6, and don't forget, I got 8 electrons in my outside shell. That's the maximum number, so we got to jump out. So we jump out and we put 4s1. So now count them: 10, 11, 12, 18, 19. There's 19 electrons. This is the valence shell. It's got 1 electron. Dash in this would be 2, 8, 8, 1. And there is the 1. So if you have 1 electron in the outside shell you have to be in group 1. All right? Now, in group 1, these are all metals. All these, lithium, sodium, potassium, rubidium, cesium, and francium, they're all metals. What is hydrogen doing in group 1? Well, first of all, you see that it's kind of split off from group 1. But hydrogen is a gas. These other ones are metals. Why in the world would hydrogen be in this group 1? Well, H1. So 1s1. So look at 1s1 in the first shell, it's got 1 electron. That is the valence shell for hydrogen. That's why hydrogen is put in group 1, because it's got 1 in the outside shell, but it's split off because hydrogen is a gas and the rest of the elements in group 1 are metals. Okay? All right. Now, something very important. The group numbers signify how many valence electrons. So watch how this works. If you are in group 1, you have 1 electron in the outside shell, 1 valence electron. If you're in group 2, you have 2 valence electrons, or 2 in the outside shell. Now we go to the transition elements. We'll talk about them later. Group 13, 3 electrons in the outside shell. 14, 4 electrons. 15, 5 electrons. 16, 6 valence electrons. 17, 7 valence electrons. And finally, group 18 has 8 valence electrons, and that's what every element on the periodic table wants to strive for. It wants to have 8 in the outside shell. Now, we talked about the transition elements in our last video. The reason these are a little strange is because these have 2 overlapping valence shells. And the 2 overlapping valence shells gives these guys multiple oxidation states. Like manganese can lose 2, lose 3, lose 4, or lose 7. Gold can lose 1 or lose 3. So these are multiple oxidation states, overlapping valence shells, and these things have backfilling. And we talked about that already. Now, the other thing we didn't talk about is all the ion solutions for the transition metals are colored. All right? All of them have color. So that's weird. If the solution doesn't have color, it's got to be either from group 1, 2, 13, 14, and so on. If the solution does have color, it's got to have an ion from the transition metals. Now, the next thing we have to talk about is the atomic radius, or the size of metals, compared to the atomic radius or size of nonmetals. So we're just going to pick one. We're going to pick sodium. So sodium, Na11. It's got 11 protons, 11 electrons. Configuration, I'm just going to do the dash now. 2, 8, 1. Now, remember what I said? Every element wants to have 8 in the outside shell. Well, here's the outside shell. So here's the deal. Do you think this atom wants to gain 7 to have 8 in the outside shell? Or would it be easier to lose 1? Well, it would definitely be easier to lose 1. So here's how we should write this. Na with a neutral sign up there, that means an atom minus 1 electron yields Na plus. Now, we are losing a negative, which means we have 11 protons, which are positive, and now we only have 10 electrons. That's why it turns positive. Now we got to see which one's bigger. Here's the atom. That's the atomic radius. This is an ion, so that must be the ionic radius. So which one is bigger for a metal? The atomic radius or the ionic radius? Well, the atomic radius is bigger. Because if you lose weight, you get small. Well, this atom lost an electron. It got small. So the atomic radius in a metal is bigger than the ionic radius in a metal because it lost an electron. So that's metals. All metals, the atomic radius is bigger than the ionic radius. Now let's go to nonmetals. Let's take oxygen. O. O has atomic number of 8. So it's 2-6. So oxygen has 6 electrons in the outside shell. What would be easier, losing 6 or gaining 2? Well, obviously gaining 2. So we have this, O, neutral, and it's going to go like this, plus 2 electrons yields O minus 2. Now, this is the atom, this is the ion. So, the atomic radius of oxygen compared to the ionic radius. Well, the ion of nonmetals gain electrons. So if you gain weight, you're bigger. So the ionic radius of nonmetals is bigger. Exactly opposite of the metal. So the ionic radius of nonmetals is larger than its atomic radius. You just got to remember, if you lose electrons, you get smaller, like metals. If you gain electrons, you get bigger, like nonmetals. Okay? All right, we're going to still talk about size. So, if you get out these that I gave you, the very large periodic tables, you've got a lot of room in the lower left, and you have a lot of room in the upper right. So we are going to compare and contrast lower left elements with upper right elements. Okay? So if you get these out, we're going to talk about what happens to size going down a group. So, look, this is period 1, 2, 3, 4, 5, 6, 7, or you could also call it shell or energy level 1, 2, 3, 4, 5, 6, 7. So every time we go down one element in a group, we gain a shell of electrons. So it's like hydrogen would have 1 shell of electrons. Lithium 2, sodium 3, potassium 4, rubidium 5. So as we go down any group, the size of the atoms gets larger. They get larger because they're gaining an energy level or a shell of electrons. So the biggest atoms in any group are at the bottom. The biggest atoms in any group are at the bottom. Okay? Because we're gaining shell after shell. So what I want you to write down in this lower left on your paper down here, I want you to put down largest atomic radius right there. Largest atomic radius. And you're going to write it underneath francium. Largest atomic radius. Now, going down is no problem because you know they're gaining shell by shell, so they're definitely getting bigger. Now, the bigger the atom, the easier it is to lose the valence electrons. Because think, the further you are away from the nucleus, the easier you are going to be to get picked off by some other element. Okay? So the absolute biggest element on the periodic table is francium. That's the biggest. So that's the easiest to get ripped off. Now, the easier it is to rip off the metal, the more reactive it is. So, what I want you to write down here, after you write down largest atomic radius, I want you to write down most reactive metal. Down here near francium, most reactive metal. Because it's really huge, fat atom, and it gives up its electron very easily. Now, the crazy part about it is, this group 1 These elements are never, ever, ever found in nature because they're too explosive. They're always found in compounds. So if you put a group 1 metal like sodium, sodium cuts like hard butter, and it's silver. And these metals in group 1 are really weird because they float in water. But if you put any of this group 1 metals in water, they explode. And so it gets more reactive all the way down to francium. Now, also the same thing in group 2. Group 2 metals are never, ever, ever found in nature by themselves because they're also too explosive. So the easier it is to lose an electron, the more explosive the metal is. So the most explosive metal on the whole periodic table is francium. The most explosive metal on the periodic table. Remember, the bigger the atom, the more metallic it gets. So even over here, like even if we start with nitrogen, which is a gas, and then we go to these other things that are nonmetals, way down here, bismuth, that's a metal because it's so big. So going down any group, the most metallic elements are always found at the bottom. Always found at the bottom, most metallic elements. Now, we talked about going down any group. The next one is really difficult. What about going across a period or energy level or shell? So look what's happening here. We're going from 3 protons or electrons to 4 protons or electrons to 5 to 6 to 7 to 8 to 9 to 10. But the deal is we are not gaining a shell of electrons every time we go over one. Going down, we gained a shell every time. That's why they got bigger going down. But going across, we're staying in the same shell or energy level. We're just getting more electrons in the same shell. So here's what I tell my students. We start out with lithium is a big atom. We move over one, we got another electron and another proton, so they pull each other in. So as we go across, the size of the atom goes like this. It gets smaller. So the size of the atom going across a period gets smaller because we get more electrons in the same shell. So the nuclear charge, the proton charge, is pulling in the valence shell. That's what's happening. So this is very weird, but going down a group, the size of the atom gets bigger, but going across a period, the size of the atom gets smaller. So remember we put down largest atomic radius here? Well, up here, near helium, I want you to put down smallest atomic radius. Where we put most active metal, down here, we're going to put down most active nonmetal right here. Now, I am definitely not looking at helium when I say most active nonmetal. I am looking at fluorine. And I call fluorine the Rambo of all elements. I don't know if you remember Rambo, but Rambo was a rough, tough special forces guy. So fluorine is the Rambo of all elements. It only wants one electron, and it's willing to rip off just about anybody to get it. And remember, fluorine is small because as we go across a period, the size of the atoms gets smaller. So fluorine is small. Its valence shell is kind of close to the nucleus. It only wants one electron, so it is wickedly strong in grabbing that electron. So now you know this. Going down a group, the size gets bigger because they're gaining shells. Going across a period, the size gets smaller because the nuclear charge or proton number is pulling in the electrons in the valence shell. So we're staying in the same shell going across. All right? So if you get out your reference table and turn to reference table S, and you look at francium, its radius is 242 picometers. And we discussed, picometers before. 242, that's the biggest on the periodic table. If you look over here at helium and fluorine, helium is only 37. Fluorine's about 60. So these are the smallest elements. These are the largest elements. And one more time, as we go down a group, the size gets bigger because we're gaining shells of electrons. As we go across, it gets smaller because we are gaining electrons in the same shell and it's being pulled in by the protons. So that's how size works. So after figuring out the size going down and going across, we have to understand this important term, electronegativity. All right? This is a biggie in the periodic table. Electronegativity. So electronegativity is the ability of an atom to attract. The ability of an atom to attract So electronegativity is the ability of an atom to attract valence electrons. This is really important. So let's figure it out. Well, what type of elements want to attract valence electrons? Well, do metals want to attract valence electrons? Well, let's see. Metals want to lose electrons. So they must have kind of lousy electronegativities. While nonmetals, most nonmetals want to gain electrons. So they probably have a stronger electronegativity. What about the noble gases? They already have 8 in the outside shell. They're super cool. What about their electronegativity? Do they want to attract? So chances are the noble gases don't really want to attract any electrons, so their electronegativity is probably nothing. So now if you look at reference table S, there is a column devoted solely to electronegativity. And the largest electronegativity of all the elements on the periodic table, the largest element with the highest electronegativity is our friend fluorine, which I said is Rambo. So the electronegativity values vary from 0 from the noble gases to 4. So the highest electronegativity is 4, and that is for fluorine, because that only wants 1 electron. Now, the metals, remember from the staircase down, they don't want to gain electrons, so they have very low electronegativities. And remember, as we go down a group, if the atom gets bigger, it's easier to lose an electron, much harder to gain one. So, down here, where you wrote down about the size, you're going to write down this. Down here, you're going to have to put down lowest electro. Now, we are going to abbreviate electronegativity because I hate spelling it all the time. So electronegativity turns into electro. So you're going to put down lowest electro right here. Because you know francium is the biggest, fattest atom. Its valence electron is way out there. It certainly doesn't want to gain any. So this has very low electronegativity or ability to attract. Whereas over here, fluorine is small. It's got 7 in the outside shell. It only needs 1 more. So this, you're going to write here, highest electro, and that was written right above the element fluorine. So, now watch. Going down any group, the size of the atoms get bigger. So if the atoms get bigger, it's much harder to gain electrons. So going down a group, the electronegativity decreases. Going across a period, since the atoms are getting smaller and they're getting more nonmetallic and they want to gain electrons, going across the periods, the electronegativity goes up. Okay? So that's electronegativity. And remember, the noble gases, most of them have 8 in the outside shell. They don't want to gain any. They don't have any electronegativity at all. All right. So that's electronegativity. So let's just talk a few numbers. Let's just talk about a few numbers about electro. Going down a group, they get smaller. Francium has electronegativity of 0.7. All right. Fluorine has an electronegativity of 4, the largest. Some of the noble gases have no electronegativity at all. Now, these guys on the staircase, B, Si, Ge, As, Sb, and Te, all these guys on the staircase, they are called metalloids. And they have properties of both metal and nonmetal. It's like a demilitarized zone between the metals and the nonmetals. You got to have a zone. You can't just go from metal right to nonmetal. So it goes metal, nonmetal, to nonmetal. That's how they go. Now, if the lowest electronegativity is 0 and the highest is 4, and these have properties of both, chances are the metalloids are going to have about 2 for the electronegativity. Right in the middle, between 0 and 4. Just about 2 for all the metalloids. So there was a question raised by one of my students about fluorine. Why is fluorine the most electronegative element like Rambo? Why? Why not chlorine or bromine or iodine? Because fluorine, chlorine, bromine, and iodine are in group 17, which means they have 7 valence electrons. All of those elements only need 1 electron to become stable. Why is fluorine the strongest? Why can it pull in electrons better than chlorine, bromine, and iodine? Simple. Fluorine only has 2 shells. So the second shell is the valence shell. It's kind of close to the nucleus. So the nucleus is holding that second shell in pretty close. While chlorine has 3 shells, bromine 4, iodine 5, so their valence shells are further out. So the stronger the nucleus holds the valence shell, the easier it is for that element to rip off an electron. So that's why fluorine is the strongest electronegative element on the periodic table. Even though these only need 1, this is small and it can rip off just about anybody.